my name's Anisha, and today we will be going over mass spectroscopy, specifically time of flight mass spec. This is part of AS and A-level chemistry for AQA, and it comes under the atomic structure topic, which is one of the first topics in the spec, I believe. So mass spec is used for two things. It's used to find the abundance, which means like the weightings of an isotope and the mass of each isotope in an element. This means that we can use that to find its AR, or the relative atomic mass, or it can help us find the relative molecular mass of a substance. The overall process is split into 4 stages. The 4 stages are ionization. This is done in 2 ways: electron impact or electrospray ionization, and then acceleration, flight tube, and detection. We'll start with ionization, specifically electron impact. Electron impact is used for elements and substances with a low formula mass. So the process starts off with the sample is analyzed by being vaporized, and then high energy electrons are fired at it. The high energy electrons come from the electron gun. The electron gun is basically a hot wire filament, but it has a current running through it, so it's able to emit those electrons. The electron gun usually knocks off 1 electron from each particle, forming a 1+ ion. So then the positive ions are accelerated by a negative electric plate afterwards. The next ionization, the other ionization technique is called electrospray ionization. So this technique is used for many substances with a higher molecular mass, including many biological molecules such as proteins. This is known as a soft ionization technique, and fragmentation rarely takes place. Fragmentation is just where the molecular ion often breaks down into smaller fragments, which are also detected. However, it's not on the spec, so you don't have to know it specifically. The sample X is dissolved in a volatile solvent and injected through a fine hypodermic needle to give a fine mist. The tip of the needle is attached to the positive terminal of a high voltage power supply. Particles are ionized by gaining a proton from a solvent as they leave the needle, producing ions with a single positive charge and a mass of Mr+1. The solvent evaporates while the ions are attracted to the negative plate where they are accelerated. Okay, so moving on to part 2, acceleration. The positive ions are accelerated using an electric field so that they all have the same kinetic energy. Given that all the particles have the same kinetic energy, the velocity of each particle depends on its mass. Lighter particles have faster velocity and heavier particles have a slower velocity. That's all there is to acceleration. It's just where the kinetic energy is all the same, so that the only factor that differentiates everything is how fast the velocity is. So the next stage is the flight tube. The flight tube is where the positive ions travel through a hole in the negative charged plate in a tube. The time of flight of each particle through this flight tube depends on its velocity, which in turn depends on its mass. The diagram here shows the ions of the 3 isotopes of magnesium, and it shows that they will travel at different speeds through the flight tube and separate, with the lightest ion, the 24 Mg+, reaching the detector first. Stage 4 and the final stage is detection. Detection is where the positive ions hit a negative charged electric plate. When they hit the detector plate, the ions are discharged by gaining electrons from the plate. This generates a movement of electrons, and an electric current is measured. The size of the current gives a measure of the number of ions hitting the plate. After detection, a computer will produce a mass spectrum, which is the graph shown here. This shows the mass to charge ratio and abundance of each ion that reaches the detector. Given that all ions produced by ionization have a 1+ charge, the mass to charge ratio is effectively the same as the mass of each ion. So in the following example, the mass spectrum of magnesium is shown. Ions with mass charge ratio 24, 25, and 26 reach the detector. This shows that magnesium is made up of 3 isotopes, Mg24, Mg25, and Mg26. Use this graph to work out the relative atomic mass of magnesium. To find the relative atomic mass, you'd have to do the combined mass of all isotopes divided by the combined abundance of all isotopes. So for this question, you'd do 79 times 24, add 10 times 25, add 11 times 26, and that would all be over 100, because when you add the abundances up, they add up to 100. And so your result would be 24.3. So the AR of magnesium would be 24.3. That is all there is to mass spectroscopy. Initially, it is a lot of information to take into account, but the process is quite self-explanatory with the names they've given. So hopefully that was useful to you, and thank you very much for watching.